Hey calculus class, I decided that I'm going to extend the due date to your project to the 22nd instead of the 18th, mainly because I have other projects coming in that day, but also because on Moodle, on the last week, I have it labeled as that day, so I didn't want to confuse you. I wanted to be consistent. So anyway, that's the new due date that's going to be there. So part of what you have to do here when you're doing the project, the big thing is the Excel component of it. And so when you get to that, you are trying to find the solution, like where this thing crosses, okay? And so here's the function, e to the negative x minus log x. And you would have to approximate that. Like if you tried to solve this, if you tried to set it equal to 0 and solve, you'd get e to the negative x equals the log of x. And remember, how do you solve exponential equations? You bring in logs when you have the log on the other side. So to isolate this x, you need a log. Well, that would put two logs around this x. To isolate this x, you need e's, and that would put another e to a power on this side. So it just would never be able to be solved algebraically. So the only way you could do it is numerically solve it. And so that's the reason why we have methods like Newton's method. Now I'm going to give you another problem with this example, because I want to go through how to use Excel for this. So I've got here a function, all right, and there's it's 0, and that's what we're going to be trying to approximate. And our precision, if you notice, like this would not work on your project because the approximation has to be to 7 decimal places. So just simply graphing it with Desmos and clicking on it is only giving you 3. So you're not going to get, you wouldn't get credit for that. That's not enough. A couple of things to do the types of little visualizations I'm going to do. Again, use f of x notation with Desmos. But let's say that I don't know what this number is. And let's say that I guess 2 is the number. That's my first guess. So I'm going to put a little table in here. Now I'm going to switch this to Excel in just a second, but I just want you to see a visual of this, of what this process is. Alright, so 2 and then f of 2. That's my original value. Okay. Now what I'm going to do is I'm going to make a tangent line there. So my tangent line is the derivative, so f prime at 2, alright, x minus 2, and then plus f of 2. Again, that's always the way that you can get a derivative at a point. I'm going to make this line blue just so that I have a contrast. Alright, so that's tangent just right there at that point where it intersects. And that tangent line hits right down here at 2.77. So that's going to be my next guess. Sorry, 0.277. Now I would need more decimal places if I was doing this in Excel, and Excel will give you more decimal places. But now we're going to let that be our point on the graph. So we're going to now look at that and f of 0.277. So that was our first guess, or right there. That's obviously not the root. That's what we're trying to guess. That was our first guess. That's our second guess. Okay, and we're going to do the same thing. We're going to come up with what is the tangent line at this number. All right, and now we got a tangent line there. And where does it hit? It hits right here. So now that's our third guess. The root of the tangent line. The tangent line is always pointing us to a better guess. So 0.925, and then f of 0.925. So what's happening is, you can see our y-coordinate is way up here above 4. Our y-coordinate is at negative 1.5-ish. So 4 in absolute value, 1.5, absolute value less than 1. Right? And we just keep doing the same thing. So this would become 925 everywhere. And now you can see I'm having to zoom in a lot just to see that there's separation between these two numbers. There's the tangent line. If I click on the blue, where does it cross at 0.7488? And if I plug in f of 0.7488, we're just barely above the axis now. All right. And then again, same thing. We're just going to grab this number and paste this. So this is how we visualize. This is how we visualize Newton's method. All right, and then finally, I mean, the blue and the red are so close to being on there. Let me just click that. So I can just click the blue. 7.7451. I'm going to take that off. Click on the red, and so you can see that we basically have it now. Okay, so that's the process here. That's what we're doing with this procedure, is we are taking guesses and using tangent lines at those guesses to get to better guesses, until eventually our guesses are, right on top of what, where they need to be. So that's the idea. That's Newton's method. Now, when you're doing Excel to get Newton's method, so if you look at what I tell you to do is the log of your birthday. So the natural log of the natural log of that number. So I'm just hypothetically saying if that was your birthday, April 19th, 1997. So you type in the natural log of the natural log, and then you would just type in your birthday with no slashes or anything like that. Okay, and you can hit, oops, I didn't close my parentheses. So you hit enter. It's always going to give you a number between 2 and 3 for all of these. So that's my original guess. Now so that's what you guys are doing, that function on the project. I'm still doing the one right here from my example, because this is the function. When I go to f of x, I'm going to, every time I see an x show up in the model, I'm going to click on this guess. So to get this to work, I basically start on the other side of f of x. So there's f of x and then equals. So in the box, I'm going to start with equals x squared. This is x. The guesses are x. So x, shift 6 for the caret, squared. So there's x squared. And then minus, start typing cosine. It'll pop up as an option here, cosine. And then inside is 2 times x. So again, there's my x. So 2 times x. And don't forget to put the little times symbol in there. All right, close the parentheses, and then minus e to the negative x. So you can't just use e here. Like if you just type e, it starts giving you these commands. So you can't do like e to the power of. You actually need this guy right here, exp. That's e to a power. And then inside of there I need negative x. So a negative sign, and then I can click the number. Close that off, and there's my function output. Alright, and if you look at what we did on Desmos, if I did 2.365123.5, there's that 5.2, the same number. Okay, so it's the output. Now this just says f of 2, f of these numbers, but that's my guess. And so that's the number that that I need in there. Now f prime, I need to take the derivative of this. So you'd have to go through line by line. What's the derivative of, I'm going to call it g. What's the derivative of x squared? It's 2x. Alright, minus cosine. What's the derivative of cosine? Derivative of cosine is negative sign, so minus negative would be plus. Sign, don't change the inside. Chain on the derivative of what's inside. So I'd have a 2 right there. Alright, then what's the derivative of e to the negative x? That's negative e to the negative x. And once again, there's a negative already there, so plus e to the negative x. So there's my derivative. Okay, so same thing. if I'm going to type this into Desmos, I need it the same thing. Everywhere I see an equal sign, I need to type that in here, and then all the stuff after. So 2 times x. So 2 times, this is still my x, plus 2 times the sign of 2 times x. Alright, close that off. And then plus, once again, we need exp for e to the power of. And negative x. Alright, and if I go down, oops, not there. If I go down over here to the next line, and I type in, this is the derivative, so if I type in g of my guess, 2.365. Alright, so now that I have that, there is no, for the first guess, there is no difference from the previous guess because there is no previous guess here. So I'm just going to gray that out. You don't have to do anything underneath here. That's just stating what the tolerance is. That lets you know when to stop. So in this cell underneath the first guess, that's where we're going to make our new guess, our second guess. And that's Newton's method. So the assumption is you derive Newton's method in the first part and you did it correctly. And whatever you get for Newton's method, then that's what you're going to click here to get your new guess. So like if you, for instance, if you think Newton's method is the old guess times the derivative plus f of x, then that's how you would get your new guess. You would just click whatever you get for Newton's method in there. Now, obviously that's not it. But whatever you think, which you derive for Newton's method, you would click the corresponding cell where that value is. And Newton's method just uses these 3 numbers to come up with your new guess. So if you've got it correctly and you click them in the correct order with the formula with the correct operations, then you'll get the correct new guess. My correct new guess, why did I start with a 2? I started with 2.36, but it should be somewhere in the vicinity of that, since that's kind of in the vicinity of 2. So I'm going to type it in so we can see what we get. So there's what I get for my next new guess. I'm going to give a little bit more room for the derivative decimal places. Here's why we do this with Excel. This has got commands in there with my guess being A2, with my value for x being A2. Well, now my value for x is A3. So all I have to do is just drag this down, and now it's got A3 in there. If I take the derivative, it was evaluated when x was the number in A2 cell. If I click on that little square right there and drag this down, now it's evaluated with A3 in there. Alright, it updates the formula for the cell. Alright, now there is a previous guess, so I need to subtract these. So I'm going to do equals absolute value. We want to make sure, because this is a positive number, we want to do the absolute value just in case one's bigger than the other, and that can happen. So our new guess minus our previous guess, how close are they? 1.94. Definitely not within our tolerance. So we'd have to do it again. Now you may be thinking, oh God, this is going to take forever. But here's what we just did here, dragging these cells down, can now be done with this entire row. So I can highlight this entire row, drag down. Alright, I can see that I'm still not within the tolerance, but that's my new guess. I can drag it down again. I'm still not within the tolerance. Drag it down again. And what's going to happen is these guesses are going to start settling down. And you can just cut to the chase and drag straight down. And right there is the time that we achieved our tolerance for the first time. Nope, sorry, actually right there was when we achieved it for the first time. And I could have done that immediately after this row was made. So what I mean by that is, if I delete all of that, this row had formulas everywhere, right? If I just highlight straight across, drag down, it immediately populates all these cells with the right numbers, with the right values clicked. All right, and again, you want to get the first time that our difference between the previous guess was below this. So that's 1, 2, 3, 4, 5, 6 leading zeros, so 10 to the negative 7th. So there's 10 to the negative 8th. That's the first time that we got it. So there is my best guess for the root, is that number right there. And again, if we look at that that solution, 7451, 7451, that's what we just found. We found it from more accuracy though than Desmos can do. So I need 7 decimal places accuracy is what that's saying. So 3, 6, there's the 7th decimal place. So I would round it. In this case, I would truncate, I would round down. And that would be my solution. Anyway, I wanted you guys to see an example of how to do it. You are going to have to take a derivative accurately as part of this to be able to know what you need to click. But all I do is take my original function, my derivative, and everywhere I see an X, I click the cell that has the X's for that row. All right, everywhere I see an X in the derivative, I click a cell that has the X in that row. And that's the key thing here. Get those first 2 rows done, and then just drag and highlight the values in the second row all the way down until you know, with Newton's method you only need like 6 rows really to do it, typically for any level of precision you want, except for the part when it goes wrong. Alright, so the part when it goes wrong, when you go down to the part when it goes wrong, your function changes. So it's no longer the function you had before. So now instead of this function, I have x cubed. So again, there's my x cubed. Okay, so I've updated it. So it's got the x cubed minus 3x squared minus 2x plus 4. Alright, and then the derivative of that's going to be 3x squared minus 6x minus 2, right? That's a polynomial, so just the power rule. So that's what I've got there. And again, everywhere there's an x, I'm just clicking that x cell. Okay, now I'm going to make the original guess 2. So after I made it 2, all this changed and updated. And I don't want you to see it because I want you to do it. But something strange happens, and that's what I want you to see here. I want you to use Excel here. You don't have to go through and do Newton's method by hand. I want you to do Excel. But what happens with your sheet? What happens if you drag down? What happens if I drag this down for rows and rows and rows and rows and rows? Alright, so look at the name of it when it doesn't work. So something's going to happen. It's not going to converge. This difference between previous guesses is not going to get better and better down below this tolerance because it's not working. So you should see, if you've done it correctly, if you've got Newton's method correctly, with this guess, with this function, you should have something obvious happen with your guesses. And no matter how far down you drag, that same thing keeps happening. So I've covered it up so you can't see it, but I want you to come up with an explanation with this. All right, and it says use complete sentences as if you're in college because sometimes people write something very vague there, and I want to make sure that you're understanding that you need to explain yourself very precisely what's happening here. So it should be something that's easily put into words and you can put in there. Now, when you get to this graph, I'm fine if you want to, with the Word document, if you wanted to delete it and like replace it with a Desmos window with this range. It's completely up to you, but you can also print this out and actually hand graph this in there. It's up to you how you want to do it, but you can use Desmos and cut and paste your Desmos picture in there and explain what's going on. So we made our original guess 2, so that means we're going to find the tangent line right here at 2 f of 2. I'm going to plot that on there just so you can see. There's our point on the graph, and we're going to make a tangent line there. So again, once again, this is tangent line notation. If you've used f notation, f of x notation instead of y, I can come up with the derivative 2 is the tangent line slope, right? And then just x minus the number that I'm picking, 2, and then plus the y coordinate there, which is f of 2. That's the tangent line. And so on Excel, on the sheet you're doing, you should get the new guess is the x-intercept of this tangent line, so the new guess is going to be 0. Alright, so I'm going to do the same thing I did here. I'm going to label the origin as 0. Okay, so I'm going to plug in 0, f of 0, and again, what do I do with my new guess? I find the tangent line equation and find where the tangent line intersects the graph. Now, you're doing this with Excel here, so there should be again an obvious pattern with the guesses going on here. But again, now we are explaining why it's happening. Why are we seeing these this crazy pattern with the guesses? So I'm going to do the same thing I did here. I'm going to grab this tangent line equation, and now my new guess is at 0. Let me make this tangent line like orange. I haven't used orange yet. But now I'm going to do it at 0. So if I plug in 0 here for all these, what do we do with these tangent lines? I'm going to dash them because they're not technically there. They just guide us to our, so we made a guess at 2, we hit here and it guides us to our better guess. This is our new guess. So we go up here, we find the tangent line, we find a better guess with the tangent line's intercept. What's the tangent line's intercept? And why is that a problem? And can we ever escape that problem with what we see here? And if you can see it, there should be a very obvious pattern that's happening here that explains the pattern that you're seeing here. Okay? There needs to be a key word, right, when you're explaining why this is happening. The visual is supposed to reveal a key word that is literally at the heart of why we're seeing this. All right, I'll give you a hint. The keyword starts with the letter P. Okay, and it has to do with an adjective that describes these tangent lines. All right, so that's all I'm going to say about it. But that should be something on the visual part of your demonstration there. And that's what I'm saying. You can also just take a screen capture of what we just saw and replace that. Okay, if you want to get this window right in Desmos, you just click the wrench tool and then you just make the numbers match up. So -441, that's these numbers here. So -441, and then the other one is -661. So you could do that here. And now you've got the window that's needed. And you could just grab all of that. You could screen capture it and throw that into your project in that pictures place. So I could delete that, paste that screen capture, shrink it down to where it's not taking up too much space. You can also right click these and do wrap text tight, and that way it's able to have the text go around it. And then you just type out your explanation, including that word that starts with the letter P that describes those lines, those tangent lines. All right, and then the other part is we can't be near a horizontal tangent line. And remember that a horizontal tangent line are like these places right here. So if I did -0.291, all right, minus is a plus, but hopefully you can see why this would be problematic. All right, I'm supposed to guess the the 0. That's why I'm trying to get the 0. And if I make that my guess, where that horizontal tangent line is, that's a big problem. And that's what you need to talk about right there. Okay, a mathematical reason based on the formula, and then just this visualization, this geometric region, based on what tangent lines are supposed, what we're supposed to do with this tangent line. All right, then it also talks about why you can't be close to this. And I'm going to make a variable a here, and I'm going to make a go between like a -0.2 0.1 and positive 0.1. And that's what I'm adding and subtracting to this. So it's like moving a little bit off of that point, right? You see? And I'm going to do the same thing here. I'm going to add A, and add A. Now this is the tangent line, right? Where do these tangent lines hit? If I zoom out, where do they hit? You know, that one hits there, okay? And then this one hits over here. All right. If I'm trying to guess this 0, and I guess something really close to these places where there's a horizontal tangent, where are those tangent lines going to hit here? And why is that going to be a problem if this one hits out here? Why is it going to be a problem if this one hits out here if I'm trying to find this 0? All right, that's what this last part right here talks about. Okay, adding and subtracting a tenth from those critical values. So I got my critical value at negative 0.291. You need to find it with more decimal places, but if I add and subtract a tenth, the hope is that you can see what's happening when I move off of that a little bit. Where do these places hit? What coordinates do I hit? And why especially that's a problem for that middle 0 there.